All right, everybody, let's dive into centroids of volumes. All right, so we want to look at the centroid of three-dimensional objects. And the centroids of three-dimensional objects are going to be very similar to the centroids of two-dimensional objects. Remember, with two-dimensional objects, we assumed a uniform mass distribution and a flat surface, basically infinitely flat. But, like a piece of paper is basically infinitely flat. So in volumes, we're going to continue to assume at least a uniform density, and I'll talk a little bit more about that later. But for now, if we want to look at the centroids of a volume, we're going to assume the density is relatively uniform. And then the equation is really not much different than it was for areas. The only variation is going to be what? So the integral of x dA, that was what we had when we were integrating over areas, but we're going to integrate over volumes now, and we're going to divide by the net volume, or the integral of d volume. Okay, so I can do similar things for y, and of course now I'm in three dimensions, I'm going to have z, right? So that's going to be the same basic idea. The difficult part here is that d volume, if I take like an arbitrarily shaped volume like my arm, and I would take one of these little squares on my shirt and then also go in and out, that would be the d volume, right, of my arm, and then I got to integrate over this nasty shape, right? So the idea here is that you're going to do three-dimensional integrals, and we want to avoid that as much as we can. Then when we extend this to the next step, we're going to look at centers of mass. And in the case of center of mass, I'm going to do the same thing, but in this case, it's going to be the integral of x dm over the integral of dm, where I'm integrating over the entire mass. Now, if there's a uniform density, this is basically the same as that, but sometimes there's not a uniform density. All right, so you integrate over a mass, and that becomes really interesting. Instead of that little cube that I took out of my arm, instead of calling that d volume, I'm going to call that dm, the little bit of mass, that little portion of my arm that is that little bit of mass that I've taken out there. Right, that's going to be dm. And then we can also extend that further then to center of gravity. And it's the same equation now, except it's going to be x dw, where dw is weight. Well, this is really no different than dm times g. So I have a g up here and a g down there. So center of gravity and center of mass are really the same thing. Okay, so that's what we're going to do with volumes, right? So a couple of things that are really interesting. If I take a volume and I spin it, if I freely spin it, so I don't force the axle, but if I freely spin it, it spins around its center of gravity. Even if I spin it like a coin flip. I may have showed this in a previous video, but I spin it around that center of gravity. Sometimes the center of gravity is not in the geometric center, like in this guy right here, right? Notice it's lopsided. And in fact, the center of gravity is here. All right, so as I toss that, it rotates around that center of gravity, which is actually here. And this is basically just a block of wood, but I didn't, but the physics teacher previous to me put a piece of metal in here. And so it offsets the center of gravity from the center. But there's a really interesting center of gravity when I look at a parallelepiped, of a box shape, if you will. So if I rotate this around the center of gravity like this, right, then the center of gravity is clearly right here. Now, if I drilled a hole in here along that axis, the hole would go through the center of gravity. Then if I flip it this way, right, you can see that spinning, right? If I drilled a hole in that center, along that axle, then those two drills lines would cross, and that crossing point would be the center of gravity. But the interesting thing here is if I flip this along this long axis, right, you'll notice that it twists as well as rotates, right? If I do it this way, it's just this nice axis of rotation. Oops. If I do it this way, nice axis of rotation. It's getting late. But if I do it this way, it twists. The axis of rotation doesn't continue this way, it's twisting, right? But that center point for that twisting axis of rotation, that'll be the center of gravity. All right, so these are how I'm going to do the integrals for center of gravity, center of mass, or the three-dimensional centroid. Same ideas. An integral is a sum, right? And we'll do an example here in a little bit where we find the center of gravity of an unusual shape, but it's all based on a summation. If the density is not uniform, we got to dig into this, right? Remember that by definition, mass density I use the Greek letter rho for mass density, and by definition, that's mass per unit volume, right? So dm dv, and so this is rho dv. So all of this, I can bring this equal sign down here, and I'm going to get the integral of x dm, but dm is rho dv, and then down here I'm going to get rho dv. Well, it looks like the rho's cancel out, but what if the density is not uniform, much like it was in this case, right? Because most of this is wood, but over here I've got some metal. If the density is not uniform, it could be the density is a function of position. Could be the density is a function of position. And in that scenario, these integrations are going to be very complicated. Right? We're not going to do anything like that in this class. I have done things like that in my second semester of physics and sometimes in dynamics, rarely, but sometimes in dynamics. So we won't do that here, but maybe later on in the dynamics videos, we'll try and take a look at something like that. All right, so that's the idea coming up with finding the centroids of a volume, and we'll do an example here in just a minute. If you have any questions, please leave them in the comments below. Thank you.